Night gathers with a quiet intent, and the sky begins to breathe. There is no hurry in this breath. It is the steady inhalation of a universe that has practiced patience for billions of years. In that patience, a single thought unfurls. A star is not a flame hurled into darkness. A star is a promise kept by gravity and light. The promise says nothing extravagant. It says only that matter will fall inward and radiation will push outward, and somewhere between those two motions a lasting calm will arise. He would watch a cloud of gas drift as if asleep. Hydrogen and helium drift with dust grains that remember dead suns. The cloud wavers under its own mild weight, and every tremor is a lullaby of attraction. A passing ripple from some far explosion might touch it. A brush of starlight might warm it. The cold allows structure to gather. Molecules release their heat to the night. Pressure loosens. Gravity advances by inches. The collapse is not a plunge. It is a slow folding of a blanket that was already folded once before. The center thickens. A core appears that no eye could see. Particles meet more often. Their motions crowd. Temperature rises. The rise is not a fever. It is a careful, steeping, particle by particle, as collisions share energy the way neighbors share news by a fence. The airless quiet does not break. The core accumulates a rhythm. It hums with the arithmetic of density and pressure. The hum is not sound. It is the outcome of forces in balance at each radius. Downward pull meets upward push from the movement of particles. The word for this is equilibrium. It is an unassuming word for a profound meditation. The meditation continues. Each layer supports the next. Thin wisps become firm lanes of pressure. Radiation tries to leave. Gravity asks it to stay. The compromise is gradual. Photons are born and scattered in a maze of matter that refuses to let them go quickly. Their random walk will last as long as continents will later drift. Inside this maze, the core prepares a gentle surprise. When the temperature climbs high enough and the density reaches its quiet verdict, tunneling allows nuclei to meet and bind. The act is so delicate that nothing outside would suspect the change. There is no crack of flint. There is only a deeper steadiness. From that steadiness flows a new kind of pressure. It is the pressure of light born in fusion. It is light that knows its duty. Upward, it moves through the labyrinth, stepping from particle to particle, transformed into heat, into a slow current of energy. The current strengthens until it matches the lean of gravity. The cloud that had been falling discovers a new center that refuses further descent. The infall slows. The sway lessens. A surface forms that glows. The star is present. At first, the glow would appear modest. Around it, the cradle still swirls, remnants of dust and gas coil into a disk. The star gathers what it can and lets the rest circle. Some of that rest will become planets, but the star pays little attention. It has learned a more serious craft. It has learned to pace itself. A small star will sip its fuel for tens of billions of years. A massive star will spend lavishly, bright and brief. Both move according to the same patient arithmetic. The difference lies only in the account balance and the rate of withdrawal. There is comfort in the predictability of this pacing. The inward pull does not rage. It is consistent. The outward radiance does not flare without cause. It is steady, like a heartbeat that has found a sustainable cadence. The luminosity answers to the mass. The surface temperature answers to the depth of the layers and the ease with which light slips through. If the material is more opaque, the star adjusts. Convection takes over where radiation lingers. If the path is clear, radiation carries the load. 1,000 tiny negotiations occur each second, and yet the visible outcome is calm. Calm does not mean still. The photosphere ripples with granules of rising and sinking gas. Magnetic threads bend and relax. Spots stroll across the surface. Flares sometimes brighten the edge. Beneath these small dramas, the balance holds. The interior presses outward exactly as much as gravity pulls inward. The match is intimate. It is calculated at every point in the star, as if the universe were sketching a contour map of trust. Where the pressure falters, gravity leans a little more. Where gravity hastens, pressure stiffens. The result is restitution without panic. He might stand in a field and feel nothing of this. Yet the warmth on his cheek tells part of the story. Photons that wandered for ages inside the star take 8 minutes to reach his skin if the star is the nearest one. The journey ends in a touch that feels almost instantaneous. The long interior patience is transformed into a gentle arrival. He breathes, and plants awaken, and oceans travel in cycles that answer to this faithful pace of light. The star asks for no gratitude. It prefers persistence. Inside the core, the quiet ritual continues. Hydrogen pairs become helium. The ash of that process accumulates. The core adjusts its size. The shell surrounding it takes on more responsibility for the flow of energy. The star changes slowly enough to write calendars on the faces of worlds. No mind could witness the full arc in a single life. Yet the law behind it is clear. Where design might be expected, there is only necessity that behaves with the grace of intention. If the star is modest, its outer layers remain transparent enough to sigh the energy away in an orderly fashion. If the star is more massive, winds will begin to carry mass outward. The process resembles pruning rather than loss. The star shapes its future by letting go of what would hasten imbalance. Every release is a decision between staying bright and staying stable. This is not a conflict. It is a craft. Consider the light itself. Each photon is a messenger that knows only straight lines, yet spends almost all of its life-changing direction in the crowd. It is as if patience were encoded at the smallest scale. The photon accepts delays and emerges without complaint. When it leaves the surface, it becomes swift. When it crosses space, it becomes story. The story is not loud. It is a steady whisper that says the universe prefers rhythms over ruptures. The star does not stand against gravity. It collaborates. Gravity provides the gathering, fusion provides the reply. The reply is measured. It never exceeds what the structure can bear. If the structure begins to sway, convection rises like hands to help. If the outer layers cool, molecules form and break in cycles that smooth the temperature. Even the variations serve equilibrium. Spots release tension, flares reorganize fields. The deeper oath remains intact. In this light, a person might finally rest. The cosmos does not need frenzy to create wonder. The cosmos holds a candle in a windless room and attends to it with infinite care. To look up is to see the signature of that care repeated across the vault. Each star displays a slightly different script. Some are blue with youth, some are gold with maturity, some are red with the first hints of farewell. All of them present a lesson that is easy to overlook. Strength may be loud. Endurance is often quiet. He closes his eyes and the warmth remains. The warmth is not an accident. It began in a cradle of gas that trusted its own weight. It matured in a core that learned to push back with light. It traveled across space with the patience of a pilgrim who enjoys the walk. It arrived as a promise kept. The promise is simple enough for sleep. Gravity will hold, light will answer. Balance will write the next moment, and the moment after that, and countless moments beyond the reach of any counting. A quiet chain of understandings began in small rooms, lit by lamps and patient doubt. The question was simple enough to hide in plain sight. What keeps a star shining for so long without burning out like a bonfire in a gale? He held the question like a seed and watched it open across decades, cities, and instruments that smelled of oil and metal and night air. In the early 19th century, a glassmaker turned spectroscopist traced delicate dark lines across the rainbow of starlight. He marked them with letters and left a map no one could ignore. Those lines would become pathways into stellar interiors that no probe could touch. Soon after, two colleagues in Germany taught fire to speak its chemistry. A flame salted with elements produced colors that matched the lines in the sky. It was an unassuming miracle. Distant suns carried the same signatures as earthly substances heated in a lab. The idea that a star could be read like a coded letter took root. On an island observatory where fog could scatter light like milk, a woman sorted thousands of spectra by hand and named patterns with a discipline that refused haste. From those patterns, others would infer temperatures and gravities. In a quiet office across the yard, an astronomer measured the brightness of variables that pulsed with rhythm, and a ladder to the galaxies began to form. The canvas grew, and the question deepened. If stars were so far and so numerous, their power source could not be a common fire. No known chemical fuel could last. In Cambridge, a mathematician with a sailor's calm set the first firm scaffolding. He imagined a star as a sphere of gas with pressure changing from center to edge. according to an equation so restrained it seemed almost shy. He gave the gas an opacity and a way for radiation to carry energy outward. He guessed at how fusion might stand in for a furnace not yet understood. He compared the masses of stars to their luminosities and found a relation that felt like a key. In 1919, the war had just closed, and an eclipse expedition he led tested the bending of light by gravity. 2 years later, he turned that gravity inward and wrote a book on stellar interiors. The book entered the modern mind like a lantern, but a lantern still needs a wick. In a laboratory not far away, a physicist weighed atoms with a precision that found a discrepancy. The mass of a helium nucleus fell short of the sum of its parts. The loss was not a loss. It had been turned into energy, as if nature kept double books, and only now someone had learned to read them. In Manchester, another voice gave the hydrogen nucleus its name and showed how atoms could change their skins under bombardment. The stage was set for a new kind of fire. At the end of the 1,920 seconds, quantum mechanics turned barriers into invitations. A young theorist described how particles could slip through walls they had no right to pass. The mathematics felt like a trick, until it explained the Sunday. If protons could tunnel into each other at high temperature and density, fusion could proceed without waiting for collisions energetic enough to overcome their mutual repulsion. 2 colleagues took the hint and proposed that the quantum crossing of barriers was the missing path. The star no longer required impossible violence. It needed only time, pressure, and the small boldness of probability. Back in a basement archive stacked with photographic plates, a graduate student at Harvard cross-checked spectra against models no one else trusted. Her thesis was an act of listening. The lines whispered that hydrogen dominated by far, with helium next, and everything else a trace. The claim contradicted accepted wisdom, yet the sky insisted. If a star held mostly hydrogen, then a fusion pathway that consumed hydrogen was not just plausible, it was necessary. In 1939, a reserved theorist in Ithaca wrote the recipes in ink that has never faded. For stars with modest cores, he described a sequence that begins with 2 protons, embracing briefly as deuterium, shedding a positron and a neutrino, and later forming helium. For stars with hotter hearts, he wrote a catalytic cycle, where carbon, nitrogen, and oxygen shuttle protons around until helium falls out like a finishing note. These were not narratives for poetry. They were differential equations matched to temperatures and densities that observers had already made credible. Yet they read as calmly as liturgy. Energy emerged in small quanta at rates that could support a star for millions to trillions of years depending on its mass. The patience of starlight had finally found its mechanism. The discovery did not take place in a single room or a single year. It moved across continents and languages. Mount Wilson's 100-inch reflector gathered spectra of bright blue giants and steady yellow dwarfs and confirmed the mass and brightness relations. Yerkes defined the limits of what glass could reveal through air. Principe and Sobral set the geometry of gravity. Cambridge and Princeton set the mathematics of interiors. Harvard's plate stacks set the chemistry. Manchester and Cambridge laboratories set the nuclear ledger. Each place contributed a tone to the chord that finally sounded whole. He would have walked around the domes at dusk and felt the wood of the doors warm from the day. Inside, mirrors waited in darkness for a slit of sky. Observers froze their fingers and counted pulses of light through eyepieces that offered no comfort. The labor was repetitive. The patience resembled the very patience of the objects under study. When the paper with the fusion chains appeared, it did not arrive like lightning. It settled into a puzzle that already had most of its edge pieces in place. Once the energy source was named, the structural picture clarified. The outward radiative and convective transport could be computed because the inner engine was no longer a guess. Tables of opacities and equations of state improved as experiments refined them. The star became a solvable object in principle, yet the tone of the discovery remained tender. It had not required a grand unveiling. It had required many minds learning to be quiet in the presence of data. The human stories matter because they show what kind of attention the cosmos asks for. The spectroscopist who sorted lines by the thousands did not shout. The theorist who traced the balance through equations wrote in sentences that made room for uncertainty. The student who dared to say hydrogen rules the stars faced cold reviews and held steady. The nuclear physicist who quantified mass loss to energy did not treat it as magic, but as bookkeeping. The tunneling pioneer was surprised that the universe would allow such grace. The fusion architect arranged steps with the care of someone placing stones across a stream. In each case, calm work found calm truth. The locations themselves taught patience. Coastal weather delayed observations for weeks. Mountain air conspired with the thinness of the atmosphere to sharpen images only on certain nights. Funding ebbed and flowed. Glass blanks cracked. War interrupted conferences. Through it all, the question stayed soft and formidable. What keeps a star shining? The answer emerged as an arrangement of facts that spoke to one another. Chemistry led to abundance. Abundance led to plausible fuel. Quantum rules led to feasible rates. Structural equations led to sustainable equilibrium. Laboratory measurements led to consistent energies. No single discipline could have completed the portrait alone. There is a gentleness in how these names fit together. Fraunhofer laid a ruler across color. Bunsen and Kirchhoff deciphered the code. Annie Cannon sorted the library of starlight. Henrietta Leavitt prepared the distance scale. Eddington built the interior architecture. Aston weighed the nuclei. Rutherford named the proton. Gamow opened the barrier. Atkinson and Houtemans suggested the crossing. Cecilia Payne read the elements aloud. Hans Bethe composed the cycles. Each gesture was modest on its own. Together they formed a tradition of listening that allowed the universe to speak in a voice suited to long durations. With the engine secured, the calmness of stellar life ceased to be a metaphor. It became a calculable property. A star could now be timed by its mass and its composition. The feeling that the night was reliable gained an argument to support it. Those who looked through the eyepiece could say why the glow did not falter. Those who balanced the equations could affirm that a deep truce holds when conditions are right. Discovery, in this instance, was not a sudden blaze. It was a candle passed carefully from hand to hand until the room was lit in full. When the understanding of fusion finally settled into the minds of physicists, the revelation carried a strange tension. The process that sustained the stars was not a violent clash, as many had imagined, but an act of improbable gentleness. It was an outcome born from the uncertainty that hides beneath all certainty. The same quantum rules that allow electrons to blur around nuclei now allowed nuclei to drift through invisible walls. Fusion was not a war between particles, but a quiet crossing of boundaries. The imagination had long pictured the heart of a star as a furnace raging beyond comprehension, yet the mathematics suggested a calmness that defied instinct. The average collision inside a stellar core was not fierce enough to overcome the electric repulsion between protons. If physics followed only classical logic, no star could burn at all. The sun's core, at 15 million degrees, would still be too cool to ignite in a purely mechanical world. The fire that humans saw as a constant blaze was instead an improbable event multiplied by vast numbers. In the language of quantum mechanics, what should never happen becomes inevitable when granted enough attempts and enough time. Each proton pair in the core of a main sequence star faces a wall of energy thousands of times its own capacity to cross. Yet quantum tunneling lets 1 in 10 billion pairs slip through. That minute success rate is precisely what the star needs. Any faster, and the reaction would erupt unstably. Any slower, and the star would freeze in darkness. The narrowness of that balance feels deliberate, though it is not. The cosmos has simply learned efficiency through statistics. Stability is the arithmetic of rare miracles repeated at scale. It was difficult for early thinkers to accept this. Many resisted the idea that something as ethereal as probability could power a Sunday. They preferred to think of atomic fusion as a sudden flash, an unstoppable chain reaction. But the star is no explosion. It is a continuous conversation between chance and restraint. Quantum tunneling permits only enough energy release to hold gravity at bay, no more. In this serenity, the universe reveals its preference for moderation. In the calm press of the stellar core, hydrogen becomes helium through pathways as elegant as calligraphy. In one version, 2 protons join briefly, forming deuterium, a light nucleus with a single neutron. The event releases a positron and a neutrino, the faintest tremors of transformation. The deuterium then unites with another proton to make helium-3, and 2 of those helium-3 nuclei later merge to form helium-4, returning 2 protons to the mix. The entire sequence converts mass into radiant energy, according to a rule so simple it seems mythical. E equals m times c squared. A small mass lost in the reaction becomes light. It is the most famous equation, yet within the star it behaves without drama. It happens everywhere, always, in silence. In hotter stars, another route unfolds. A handful of carbon, nitrogen, and oxygen nuclei act as messengers, shuffling protons from one atom to another until helium forms again. These catalysts are unchanged by their labor. They exist solely to make the process more efficient. The details of each reaction are intricate, but their spirit is the same persistence through moderation. The brilliance of a star is the sum of innumerable modest events, each guided by the most delicate of permissions. The deeper implication shook science. The sun was not unique. Every point of light scattered across the night obeyed the same improbable arithmetic. The life of stars, once considered unknowable, had become a reproducible pattern. Their variety in color and brightness could be traced to a single controlling principle: the rate at which fusion proceeds. From faint red dwarfs to massive blue supergiants, all followed a gradient of pressure and temperature defined by mass. The simple scaling revealed a profound symmetry. The universe had one recipe, endlessly rewritten with slight adjustments. The surprise came in the numbers. The efficiency of fusion is astonishingly low, and yet its total effect is immense. In 1 second, the sun converts about 4 million tons of matter into energy. To human minds, that number sounds violent, but for the star, it is restraint. Out of the sun's total mass, that loss is negligible, like a grain of dust shed from a mountain each year. This minuscule rate of consumption ensures that the star will live for billions of years. The fire is eternal precisely because it burns so slowly. The stability of life on any planet depends on this unhurried miracle. The more physicists studied, the more serene the picture became. Every stellar property once thought turbulent revealed hidden order. The core's pressure gradient balances exactly against gravity's inward pull. Temperature adjusts itself in response to energy flow, and density reconfigures to maintain equilibrium. If a perturbation occurs, a rise in core temperature or a dip in pressure, the system self-corrects. A hotter core expands slightly, reducing its density and slowing fusion. A cooler core contracts, raising pressure and reigniting the process. It is the cosmos practicing self-regulation, an unconscious wisdom older than life itself. This realization reframed the emotional weight of the discovery. Stars were no longer blazing furnaces destined to consume themselves quickly. They were meditators, poised in perpetual adjustment. Each carried within it the lesson that endurance does not come from force, but from balance. The quietness of quantum tunneling, the patience of reaction chains, and the self-correcting nature of stellar interiors revealed a universe that achieves longevity through subtlety. Astronomers began to see the stars not as chaotic engines but as vast, breathing organisms. Their hearts pulsed with light, not fury. Their surfaces trembled gently, transmitting sound waves that would one day be measured to map their interiors. The old image of a violent cosmos softened into something contemplative. The sky's brilliance was not aggression. It was equilibrium manifested as radiance. The philosophical implication is difficult to ignore. If the foundation of starlight rests upon the uncertainty of quantum mechanics, then uncertainty itself is a creative force. Probability becomes the sculptor of stability. The delicate randomness at the smallest scales ensures the persistence of order at the largest. Every sunset, every reflection in a lake, every living eye owes its existence to an event that had no guarantee of happening. In the arithmetic of the universe, peace is not an accident. It is a result of countless chances choosing harmony. Thus, the scientific shock was not that stars lived by fusion, it was that such serenity could emerge from the heart of what seems impossible. The equations that govern the stars whisper that impossibility, multiplied by infinity, becomes life. What appears unstable at the human scale becomes eternal at the cosmic scale. The laws of nature reveal that gentleness is not weakness, but design. And so the understanding deepened. A star's existence is not defiance but acceptance. It yields to gravity, it yields to quantum uncertainty, and in yielding, it finds the power to shine. The cosmos thrives by not resisting its own laws. Light exists because matter learns how to surrender precisely enough. At the center of every star lies a conversation between equations, so patient they appear eternal. The story of that conversation begins with one idea: hydrostatic equilibrium. In this delicate state, gravity's inward insistence is exactly matched by the outward pressure of energy and motion within. The word equilibrium sounds simple, yet behind it hides a labyrinth of relationships. It is not a frozen balance, but a living negotiation. The star is never still. It is continuously correcting itself, adjusting pressure, density, and luminosity as if fine-tuning a long, unbroken note. The principle itself is written in the simplest of expressions. At every layer within the star, the change in pressure with radius equals the weight of the material above it multiplied by gravity's pull. This unadorned rule of balance builds the architecture of suns. If the pressure at any level was slightly weaker, collapse would follow. If it were stronger, the star would expand until its own stability returned. Out of this conversation arises a natural law of restraint. Each atom within a star contributes its push to keep the structure breathing, and together they hold the shape of a sphere that defies its own fall. Beneath that equilibrium, energy must travel. Radiation carries it through the dense interior, each photon scattering countless times before escaping. But photons are not always efficient couriers. In cooler or denser regions, light struggles to move through matter. There, convection takes command. Hot gas rises, cool gas sinks, and a slow circulation replaces direct transport. The star finds whichever path allows heat to reach the surface with the least resistance. This adaptability gives each class of star its own internal design, some ruled by radiation, others by churning currents. Yet both methods serve the same truth. Energy must flow, but never faster than balance allows. From this dynamic comes one of the most elegant relations in astrophysics, the mass-luminosity law. Observers noticed that a star's brightness grows rapidly with its mass. Doubling the mass does not merely double the light, it can make the star 30 times more luminous. The reason lies in the pressure-temperature relationship. A heavier star compresses its core more tightly, igniting fusion at a higher rate. The result is brilliance, but at the cost of time. Such stars live fast, burning their hydrogen supply in mere millions of years. Smaller ones, faint and cool, burn slowly and may persist for trillions. The relationship is precise enough to predict a star's lifespan from its brightness alone. In that mathematical intimacy, one sees that even radiance has a cost measured in patience. The equations that govern this exchange are as quiet as the phenomena they describe. Pressure comes from motion, from particles in ceaseless dance, colliding and rebounding against each other. Temperature is not heat in the human sense, but an accounting of that motion's intensity. When gravity compresses the gas, the particles move faster, raising temperature and pressure until equilibrium is restored. If energy is lost through radiation, the gas cools and contracts, reigniting fusion to compensate. A star behaves like a living regulator, maintaining its conditions without intent, guided only by the arithmetic of matter and light. The study of stellar structure advanced through thought, more than through direct observation. No probe could reach a star's heart, no telescope could see beneath its shining skin, yet mathematics became a form of vision. By dividing the interior into infinitesimal shells and applying conservation laws to each, scientists could model the unseen. Each shell contributed its own part to the larger equilibrium, linked by the flow of energy and the gradient of pressure. Solving these coupled equations required more than calculation. It required imagination disciplined by logic. The interior of a star was not simply guessed, it was derived, layer by layer, from first principles that were universal. In these derivations, another insight appeared. There exists a critical balance between radiation and gas pressure, a ratio that decides a star's destiny. In smaller stars, gas pressure dominates. Atoms push against gravity directly through their collisions. In massive stars, radiation pressure, the momentum carried by photons, becomes equally important. Too much radiation pressure, and the outer layers tremble near instability. Too little, and the interior heat cannot escape. Between these extremes lies the narrow corridor where stars can live in serenity. That corridor defines nearly all visible stars in the night sky. The universe, in its abundance, prefers balance to excess. Within this framework, every feature of a star finds explanation. The gradient of temperature sets the color of its light. The distribution of energy transport determines its texture, smooth for radiative stars, mottled for convective ones. The fusion rate at the core establishes its brightness, and the mass sets both its gravity and its lifespan. The symmetry is breathtaking. A handful of equations predict the infinite diversity of the cosmos. The very act of shining becomes a mathematical inevitability. Yet, for all its predictability, each star retains individuality. Slight variations in composition, rotation, or magnetic field create unique signatures. Rotation flattens the poles and stirs the interior, blending fresh hydrogen toward the core. Magnetic fields carve loops and spots into the surface, sculpting waves of brightness that can persist for years. Even within perfect equilibrium, subtle irregularities breathe life into the pattern. Perfection, it seems, allows space for variation. The radiative transfer itself hides an astonishing patience. Photons born in fusion may wander for hundreds of thousands of years before escaping the surface. They bounce from ion to ion, changing direction each time, transferring energy but rarely themselves moving far. The process resembles thought, slow diffusion through countless tiny decisions that eventually reach clarity. When the photon finally leaves the star, it travels unimpeded across the vacuum, arriving at distant worlds as warmth, color, and time itself. The light seen tonight on Earth began its journey before humanity existed. Such endurance turns starlight into history written in motion. Through these relationships, equilibrium becomes more than a scientific condition. It becomes a metaphor for the cosmos. Every part of the star knows its place, not through awareness, but through law. The result is neither stillness nor chaos, but a slow harmony. The structure endures because each force concedes exactly as much as it asserts. Nothing dominates, nothing withdraws completely. It is the same balance that appears in galaxies orbiting a center, in atoms bound by attraction and repulsion, in ecosystems that find their rhythm over generations. The star is the universe condensed into a single act of understanding. To those who study it, the equations become almost meditative. The star is both an object and a process, a pattern repeating itself through time without losing identity. Its life depends on conditions so specific that even minor deviations could dissolve it. Yet within those conditions lies flexibility, a willingness to shift and adapt without breaking the symmetry. The hydrostatic equation, the radiative transfer equation, and the mass-luminosity relation together describe this poise. The mathematics does not exaggerate, it whispers the truth of persistence. Thus, the hidden equilibrium is not a static miracle. It is the result of countless adjustments, each obeying laws older than stars themselves. Gravity compresses, pressure expands, energy flows, matter responds. The outcome is beauty so stable that it seems eternal. The star lives by maintaining tension, and in that tension lies peace. The equations that define it are not mere symbols, they are the heartbeat of cosmic continuity. The calm image of a star, constant and unwavering, hides a story that begins in turmoil. Long before balance is achieved, chaos governs. The creation of a star is an act of organized surrender by a cloud that once drifted freely across light years. Interstellar space is not empty. It is filled with enormous molecular clouds of gas and dust, cold enough for hydrogen molecules to cling together. These clouds are the dark continents of the Milky Way, stretching for hundreds of light years, their outlines barely visible except where they blot out the stars behind them. It is within these quiet shadows that the seeds of suns begin to form. Gravity starts the conversation. Within a vast cloud, tiny fluctuations in density create small pockets of attraction. A whisper of imbalance is enough. A region slightly denser than its surroundings begins to draw matter inward. The motion is slow at first, a descent through resistance and cold. Radiation escapes freely, cooling the material further and allowing collapse to continue. As the gas falls inward, it fragments, forming knots and filaments. Each filament winds around itself, twisting and tightening like threads spun by invisible fingers. These filaments are the veins through which gravity channels its purpose. Turbulence fills the cloud with eddies and collisions. Magnetic fields snake through it, bending the motion of charged particles, shaping the collapse but never halting it. Where gravity grows stronger, it begins to dominate, pulling the material into a compact core. The density increases and the temperature begins to rise. The core glows faintly in infrared light, though no visible fire has yet appeared. This stage is the protostar, a body half-born, gathering mass from its surroundings while still hidden within its parent cloud. Around it, the collapsing material does not fall straight in. It carries angular momentum, a subtle inheritance from the motion of the galaxy itself. As the core contracts, that rotation speeds up, forming a flattened disk of gas and dust encircling the newborn star. The disk becomes a laboratory of creation, where planets, moons, and asteroids will eventually assemble from grains that collide and stick together. But at this moment, all energy flows toward the center. The protostar's growing heat pushes outward against the infall, seeking the balance that defines true stardom. The process of birth is anything but peaceful on its own scale. Shock waves ripple through the gas, and jets of plasma burst from the poles, shooting into space at hundreds of kilometers per second. These outflows clear cavities in the surrounding cloud, carving paths through which light will one day escape. The jets are not destructive. They are the protostar's way of shedding excess momentum, of making peace with its own spin. Without them, the forming star would rotate itself apart. Even in chaos, nature practices restraint. As the core temperature climbs past a few million degrees, the energy from gravitational compression becomes intense enough to halt the freefall temporarily. For the first time, radiation pressure begins to push back. The protostar trembles on the edge of equilibrium, neither collapsing fully nor expanding into emptiness. Within its opaque body, convection stirs hot material from the center toward the surface, distributing heat like the churning of a deep ocean. This convection keeps the temperature even, preventing runaway reactions that could tear the young star apart. When the temperature finally reaches about 10 million degrees, hydrogen fusion begins. The first chains of reactions release photons that bounce through the dense interior, and the star's light slowly brightens. The surrounding disk and envelope, once opaque, begin to disperse under the force of radiation and stellar winds. What was once invisible now pierces the darkness. A new star emerges from its cocoon. The turmoil of collapse gives way to the serene glow of equilibrium. What was disorder becomes endurance. Yet scientists were puzzled by how rare this success seems to be. Not every clump of gas in a molecular cloud becomes a star. The star formation rate of galaxies, including our own, is surprisingly modest. Given the abundance of raw material, one might expect the sky to fill with new suns far faster than it does. Something slows the process, a hidden regulator within the chaos. Turbulence appears to be one reason. The swirling motions inside molecular clouds resist compression, keeping much of the gas too agitated to settle. Magnetic fields add their own restraint, threading the gas like invisible scaffolding and supporting it against gravity. Even radiation from nearby young stars plays a role, heating the surrounding material and dispersing potential birth sites. Star formation, therefore, is not a runaway cascade, but a measured unfolding. Only a fraction of a cloud's mass finds its way into stars. The rest remains as the medium for future generations. Astronomers began to see this moderation as a kind of cosmic self-control. The universe does not rush its creation. Instead, it nurtures each new star through countless subtle checks and balances. Simulations show that feedback from newborn stars, their winds, radiation, and supernovae continually stirs the remaining gas, preventing excessive collapse. The cycle of star birth and destruction maintains the rhythm of galaxies, ensuring that matter is neither hoarded nor squandered. Even the structure of galaxies reflects this discipline. Spiral arms compress gas as they rotate, triggering bursts of star formation, but between those arms lie calmer regions where clouds disperse and rest. This alternating pattern prevents exhaustion of material, sustaining galaxies across billions of years. Every glowing point in the sky is part of this slow choreography. Nothing about it is hurried. Within each young star cluster, the diversity of newborn suns already hints at an underlying pattern. Some are massive, burning fast and blue. Others are small, destined to live far longer. Their distribution follows a mysterious order that astronomers call the initial mass function, a pattern that seems to repeat everywhere in the universe. It suggests that the chaos of birth conceals an unspoken preference for certain proportions, as if the cosmos were composing harmonies rather than random noise. The birth of a star thus becomes an act of both violence and grace. Gravity gathers, turbulence resists, magnetic fields bend, radiation pushes, and through it all, a new balance is achieved. The apparent disorder conceals a hidden calm, one that only emerges when forces in opposition learn to coexist. What begins as collapse ends in poise. The darkness of the molecular cloud gives way to a quiet, shining order. In this process, the universe reveals one of its oldest truths. Even chaos is a path toward harmony. The calm star seen from afar is not born from peace, but from struggle resolved. The light that steadies the night once rose from storms of gas and time, shaped by laws that favor not speed, but endurance. Every point of light in the sky is the memory of that transformation: turbulence softened into radiance, gravity shaped into rhythm, motion turned into meaning. In the grand map of the cosmos, the patterns of stellar birth should vary wildly from one place to another. Some galaxies are ancient and red, others young and blue, some thick with dust, others nearly barren. Yet when astronomers measure the masses of newborn stars, a quiet enigma appears. Across the spiral arms of our own Milky Way, within distant dwarf galaxies, even in the early universe observed through the deepest telescopes, the distribution of stellar masses follows nearly the same curve. This is the initial mass function, a mathematical melody describing how many small stars are born for every giant. It is a law of preference written across the universe. For every massive, blue hot star born in a cluster, there are dozens of medium-sized ones like the Sun and hundreds of smaller red dwarfs. The ratios remain astonishingly consistent. No matter how different the environment, the recipe repeats. Clouds vary in temperature, in metallicity, in pressure, and in the violence of nearby supernovae, yet the final symphony sounds the same. This cosmic regularity confounds simplicity. Why should the universe favor a single pattern? The first to notice this repetition worked quietly with photographic plates and early computers, counting and comparing the brightness of stars in clusters of different ages. The pattern persisted even when the data were reanalyzed, the method refined, and the instruments improved. Later, satellites like the Hubble Space Telescope and the Gaia Observatory extended the count to billions of stars. The same law emerged, patient and unbroken. The small outnumber the large by a predictable rhythm. It was as if star formation were guided by an unseen composer who tuned the masses to fit a universal scale. Science, faced with such symmetry, began searching for its cause. Some proposed that turbulence in molecular clouds naturally creates more low-mass fragments than high-mass ones. As gas collapses, eddies break the flow into smaller pieces, each fragment becoming the seed of a star. Most fragments cannot collect enough material to grow massive before radiation from nearby newborn stars disrupts them. Others suggested that cooling efficiency sets the limit. The gas radiates away heat more effectively at certain densities, promoting fragmentation at those scales and suppressing it elsewhere. The physics of cooling, not coincidence, might write the cosmic score. Still, others turned to the influence of feedback, the self-regulating behavior of star formation. When massive stars ignite, their ultraviolet radiation ionizes the surrounding gas, heating and dispersing it. Winds and supernova shocks tear through nearby filaments, halting the birth of new giants while allowing smaller stars to form in the leftover clumps. In this way, each generation of stars sets the terms for the next. The result is a natural equilibrium. Too many large stars, and their feedback ends the process prematurely. Too few, and the clouds collapse unchecked. The universe seems to have found a balance between extravagance and restraint. The most haunting feature of the mass function is its persistence through time. Observations of galaxies billions of light years away, their light, a fossil from the early universe, show the same pattern, with only subtle differences. The laws of star formation appear to have operated unchanged for nearly 13 billion years. Even when cosmic conditions were harsher, when gas was more pristine and dense, the stars that formed followed the same statistical preference. The cosmos behaves like a memory that refuses to fade. For astrophysicists, this regularity carries profound consequences. The way galaxies evolve, the chemistry of planets, even the possibility of life, all depend on the distribution of stellar masses. Massive stars create heavy elements in their cores and scatter them in explosive deaths. Smaller stars, living longer, provide steady light for worlds to form and thrive around them. The balance between these types shapes the universe's entire history. The initial mass function is not a minor curiosity. It is the foundation of cosmic evolution. Yet despite its importance, its origin remains elusive. Some models suggest that the pattern arises from a universal scaling law hidden in turbulence. The chaotic motions of interstellar gas follow a power spectrum similar to that of clouds in Earth's atmosphere. The same mathematics that describes the sizes of weather systems may describe the birth of stars. Within that turbulence, density peaks occur at predictable scales, giving rise to a preferred mass distribution. If true, then the stars are the universe's version of clouds, structures born from randomness but shaped by deeper order. Other models explore the influence of magnetic fields, whose tension resists collapse in large regions while allowing smaller pockets to proceed. These magnetic lines act like invisible architecture, ensuring that most stars form modestly rather than extravagantly. Still others point to cosmic radiation, which limits cooling at the smallest scales, preventing an infinite cascade of tiny stars. The consensus is not yet written. What unites all explanations is the sense that the universe regulates itself with an artist's precision. The philosophical echo of this is hard to ignore. From chaos emerges uniformity, from randomness, repetition. The cosmos, which appears wild and free, arranges its children according to a quiet discipline. The same distribution that governs stars in a young nebula also governs stars in ancient globular clusters that formed before the Earth existed. Even the most distant galaxies, seen as faint smudges on the edge of visibility, reveal the same statistical fingerprint. It is as though the laws of creation hum the same tune everywhere, no matter the age or distance. The stability of this pattern offers a comfort that borders on the poetic. The night sky is not an accident of varying odds, but an organized field of consistency. Behind every glittering point lies the same rule, repeated without fatigue. It hints that the universe itself favors moderation. Too many giants, and the galaxies would burn too fast. Too many dwarfs and light would fade to cold embers. Somewhere between the two extremes lies the melody that keeps existence luminous. To look at the stars with this understanding is to sense a hidden rhythm beneath their differences. The colossal blue giants live like brief crescendos, while the countless small red stars sustain the harmony across ages. The mass function is not only an equation, it is the universe's handwriting, precise yet fluid. It reminds the listener that balance is not monotony, it is structure. The same laws that permit storms in galaxies also enforce stillness in the outcome. In this calm mystery, the cosmos speaks without words. It reveals that the act of creation is not a single explosion, but a sustained composition. Gravity, radiation, turbulence, and time together produce a pattern that repeats without fatigue. Every cluster of newborn stars hums the same chord. Every galaxy keeps the same rhythm. The mystery deepens not because we fail to understand, but because the more we do, the more elegant the rule appears. The universe's preference for harmony is not an accident, it is its nature. A star does not count its years in numbers, but in the quiet rhythm of its hydrogen. Every pulse of fusion, every photon released, every adjustment of temperature and density becomes a syllable in its lifelong sentence. The age of a star is written not in its surface, color, or brightness alone, but in the time it takes to exhaust the fuel of its heart. Mass dictates that time with the precision of fate. From this dependency emerges one of the most elegant relationships in astrophysics, the connection between a star's weight and the length of its life. If a star is light, its life is long. If it is heavy, its time burns away like breath on glass. The mathematics behind this is simple yet profound. The energy released through fusion is proportional to the star's mass. More matter means more potential fuel, but the rate at which that energy is consumed depends on luminosity, which rises steeply with mass. A star twice the sun's mass shines roughly 30 times brighter, spending its energy 30 times faster. As a result, large stars live short, radiant lives, while small ones persist in quiet endurance. A star like the Sun will spend around 10 billion years in this steady balance, an era called the main sequence. During this time, hydrogen in the core fuses into helium, providing the outward pressure that resists gravity. The surface glows steadily, the color remains constant, and the internal structure adjusts only slightly. Everything about such a star is predictable. It exists in a long meditation between birth and transformation. But for smaller stars, this phase stretches unimaginably further. Red dwarfs, the most common stars in the universe, burn their fuel so slowly that none have yet reached old age. Their lifespans exceed the current age of the cosmos itself. They will continue shining when galaxies have dimmed and time has thinned into cold silence. Massive stars tell the opposite story. Their internal temperatures soar to tens of millions of degrees, making fusion brutally efficient. The same process that allows them to shine with extraordinary brightness also ensures their brevity. They rush through their hydrogen reserves in a few million years, an instant on the cosmic clock. The brighter the star, the shorter its existence. The universe expresses patience not through power, but through moderation. Astronomers began to measure these rhythms by comparing clusters of stars of different ages. In a young cluster, the sequence of brightness and color extends smoothly from hot blue to cool red. In an older one, the upper end of that sequence is missing. The massive, luminous stars have already evolved away, swelling into giants or collapsing into remnants. By tracing which kinds of stars remain, scientists can read a cluster's age like rings in a tree. The turning points in these diagrams reveal how long stars of different masses spend in the main sequence phase. In this way, starlight itself becomes a clock, and galaxies become archives of time. Inside the core, the balance is maintained by a graceful feedback loop. As hydrogen fuses into helium, the number of particles decreases slightly, reducing pressure. Gravity tries to close in, compressing the core and raising its temperature. The increase in temperature accelerates fusion, restoring the lost pressure. This self-regulating mechanism keeps the star stable for eons. It is a perfect dance between collapse and expansion, with each step correcting the other. When one looks at a star through a telescope, that single point of light embodies trillions of such corrections every second. Even within that apparent steadiness, subtle changes unfold. The core slowly accumulates helium, becoming denser. The fusion rate adjusts, the temperature rises, and the star's luminosity increases gradually. Over billions of years, the Sun itself has brightened by about 30% since its formation. This slow evolution alters the climates of planets orbiting nearby, shifting the boundaries of habitability across time. The fates of worlds, oceans, and atmospheres all trace back to the star's slow climb toward brightness. The mathematics of stellar lifetimes condense this grand story into a single expression. Lifetime is roughly proportional to mass divided by luminosity. Since luminosity grows steeply with mass, almost as the cube or fourth power, the relationship produces a dramatic contrast. A 10 solar mass star shines 10,000 times brighter than the Sun, but lives only about 20 million years. A half solar mass star glows with less than a tenth of the Sun's brightness, yet may endure for 50 billion years or more. These ratios are not poetic exaggeration, they are the logic of physics written across light. This dependence of time on mass gives the universe its sense of order. Galaxies sparkle because short-lived giants are always being born to replace those that die. Long-lived dwarfs maintain the faint background glow that endures even when the fireworks end. The interplay of these timescales ensures continuity, a dynamic equilibrium of creation and decay. Without such diversity in stellar lifetimes, the cosmos would age either too quickly or not at all. The main sequence, though steady, is not uniform. Stars of different masses transport their energy in different ways. Smaller ones rely heavily on convection, constantly mixing their interiors so that fresh hydrogen is always available for fusion. This makes them nearly immortal in cosmic terms. They can burn almost all of their fuel before fading. Larger stars, dominated by radiation in their cores, keep hydrogen confined to a limited region. Once it is gone, no amount of mixing can replenish it. Their brilliance, therefore, carries the cost of waste. Nature's most beautiful lights are also its most ephemeral. Astronomers often express this balance in the language of color and temperature. The bluest stars are the hottest, their surfaces exceeding 30,000 degrees. They shine intensely, bathing their surroundings in ultraviolet light that shapes nebulae and sculpts the birthplaces of new stars. Yet within a few million years they are gone, leaving behind heavy elements and shock waves. The red stars, by contrast, are cool and dim, but they persist through the ages. Together they form the chromatic heartbeat of galaxies, short, bright pulses, followed by long, quiet breaths. Beyond the numbers lies a deeper reflection. Time in the cosmos is not uniform, it flows differently for different forms of matter. A human life measures seconds, a planet measures orbits, a star measures the slow exhaustion of its fuel. When one looks up at the night sky, one is seeing multiple versions of time coexisting: stars that will outlive the universe and stars already gone, their light still traveling toward us. The sky is not a picture of the present, it is a tapestry woven from many ages at once. In this understanding, the lifetime of a star becomes more than a calculation. It becomes an expression of cosmic temperament. Power and brevity, modesty and endurance, these opposites shape the rhythm of creation. The stars that die young enrich the universe with heavy elements, sowing the material for planets and life. The stars that live long preserve the quiet stability that allows those worlds to exist. The cosmos depends on both. Balance extends even to time itself. Thus, the main sequence is not merely a phase of stellar existence. It is the universe's long inhale, the interval between beginning and transformation. Each star, by simply persisting, keeps the cosmos from collapsing into silence. Their varied lifespans weave continuity into creation, ensuring that the night sky never grows empty, that light always finds another generation to carry it forward. In this steady arithmetic of years, the universe learns the virtue of patience. The light from a star carries more than color and warmth. It carries rhythm. Beneath the glow, entire symphonies of motion unfold: oscillations, ripples, and resonant tremors that move through stellar bodies like sound through an immense, glowing bell. To listen to a star is to eavesdrop on its heartbeat. The field that allows such listening is called astroseismology, and it has transformed our understanding of stars from distant points of light into living, breathing structures that sing their physics into the cosmos. Every star vibrates. Inside, waves of pressure rise and fall, driven by the continuous interaction of gravity and gas pressure. These waves travel through the interior, reflecting and refracting within the star's layers. Some reach the surface and alter the brightness slightly, while others remain trapped within, circulating endlessly in hidden chambers. These patterns of vibration, millions of tiny resonances, carry information about temperature, density, and composition. The same principle applies to the Sun, whose oscillations are measured in fractions of a millimeter at the surface. Yet from these faint ripples, scientists can infer the structure of regions tens of thousands of kilometers below. It began with the realization that the Sun flickers. For centuries, its light appeared constant, but with precise instruments, small variations became visible oscillations repeating every few minutes. These fluctuations were not random. They followed clear, regular patterns. Each mode of vibration corresponded to a distinct wave traveling through the Sun's interior. The discovery was subtle but revolutionary. The star was not static, it resonated. The Sun, once thought silent, was filled with music. Helioseismology, the study of these solar oscillations, grew into one of the most delicate sciences. Networks of telescopes across the globe recorded the Sun continuously, while satellites such as SOHO and SDO monitored it from space, free from the distortions of Earth's atmosphere. The data revealed thousands of oscillation modes, each one probing a different layer of the solar interior. From this spectral orchestra, scientists could reconstruct a detailed map of the Sun's internal rotation, density, and sound speed. It was as if humanity had invented sonar for the heavens. The technique soon expanded beyond the Sunday. With the rise of high-precision space telescopes, missions like CoRoT, Kepler, and TESS, astronomers began to detect similar oscillations in distant stars. Small variations in brightness, measured over weeks or months, revealed their own frequencies and harmonics. astroseismology had arrived. Each star became a unique instrument, its vibrations encoding a signature of its inner life. From these signatures, researchers could determine the star's age, composition, and evolutionary stage with astonishing accuracy. These vibrations fall into two main families. Pressure modes, or P modes, are like sound waves, restored by pressure forces and primarily sensitive to conditions in the outer layers. Gravity modes, or G modes, move more slowly, restored by buoyancy and shaped by the deep interior, particularly the core. In some stars, these two types of waves mix, revealing complex interactions between inner and outer regions. The detection of mixed modes was a triumph, a way to measure what could never be seen directly. The stars were not just glowing, they were speaking in tones of physics. The patterns of these frequencies tell stories about internal structure. In our Sun, the data revealed that its core rotates slightly faster than its outer layers, a gentle differential that would be invisible otherwise. In red giants, astroseismology exposed how helium-burning cores contract while their envelopes expand, a contradiction resolved only by vibration. Even white dwarfs, the dim, cooling embers of stars, were found to quiver with faint pulsations, allowing astronomers to read their internal composition like Braille. No other method could provide such intimacy with an object so distant. Each vibration begins as a small disturbance, perhaps a patch of convection pushing upward, or a shock from magnetic activity. The waves travel freely because the star is mostly fluid. There are no solid surfaces to absorb them. Instead, temperature gradients bend and trap the waves, creating resonant cavities. The frequencies that survive are those that fit perfectly within the stellar dimensions, reinforcing themselves again and again. The star becomes its own instrument, shaped by its mass, temperature, and age. In this way, every note is a clue, every oscillation a coordinate in the map of its interior. The precision of this method is almost eerie. By analyzing the spacing between frequencies, scientists can determine the size of a star to within a fraction of a percent. By measuring how the frequencies change over time, they can trace slow evolutionary shifts, the exhaustion of hydrogen, the onset of helium burning, the deepening of convective zones. Stars that once appeared identical can now be distinguished as adolescents, adults, or elders in stellar chronology. The universe's calendar becomes audible. Beyond the scientific data lies a deeper resonance. The act of listening to a star transforms our sense of distance. Light travels silently through space, but oscillation adds a dimension of intimacy. It reminds observers that these remote suns are not abstract spheres of plasma, but dynamic, resonant beings. The sun's 5-minute oscillations, for instance, carry enough energy to move its surface by a few meters. Scaled to human experience, that would be like the entire Earth breathing in and out every few minutes in perfect rhythm, yet we do not notice because the breath is light itself. In the vibrations of distant stars, we find confirmation of a larger truth. Equilibrium is never silence. Even stability contains motion, subtle and perpetual. The heartbeat of a star is not a sign of disturbance, but of life continuing in perfect adjustment. Each wave passing through its body is an expression of feedback, a reaffirmation of balance. The universe does not rest by being still, it rests by maintaining rhythm. Philosophically, the discovery of stellar music bridges science and emotion. The notion that stars sing, though metaphorical, speaks to a real physical order. The oscillations are measurable, predictable, yet profoundly poetic. They imply that creation is not static. It resonates with its own coherence. Every photon that reaches us carries traces of that vibration, the echo of pressure waves born in darkness, traveling outward until they become warmth on our skin. When astronomers translate these vibrations into audible sound, the results are uncanny. Deep hums, trembling tones, slow chords that shift over minutes or hours. They are not melodies in the human sense, yet they stir the same response. They remind listeners that sound is only pressure moving through medium, and that medium can be air or plasma or light itself. The stars, in their vast patience, have been performing this cosmic symphony long before life learned to hear. Thus, the study of stellar oscillations does more than measure internal physics. It teaches a quiet philosophy. The universe speaks through continuity. What appears silent is merely tuned to a slower tempo. To hear the stars is to understand that even constancy carries motion, that stillness is not the absence of change but its most refined form. Every vibration that travels through a star carries a message that repeats across eternity. Harmony endures not because nothing moves, but because everything moves together. As a star ages, the symmetry it once held begins to loosen. Its calm equilibrium, so long maintained between gravity and radiation, starts to tilt under the quiet accumulation of change. Hydrogen in the core diminishes, helium ash piles up, and the balance that defined the main sequence begins to strain. Yet the first sign of this slow transformation comes not from the core itself, but from the outer layers, where the star starts to breathe differently. It is in these breaths that stellar winds are born. Every star exhales. From its surface flow streams of charged particles, protons, electrons, and heavier ions, pushed outward by heat, radiation, and magnetic fields. This exhalation may seem gentle, but across billions of years, it reshapes both the star and the space around it. The stream is called a stellar wind, and it is the quiet sculptor of evolution. For some stars, it is a breeze so mild that it only trims the edges of their mass. For others, it becomes a storm strong enough to unmake the star's future entirely. The Sun provides the clearest example. From its corona, the outer atmosphere heated to millions of degrees, flows a continuous wind that extends far beyond the planets. It carries away nearly 1 million tons of material each second. Yet compared to the Sun's mass, this is barely a whisper. Even so, this gentle loss shapes the magnetic environment of the entire solar system. The wind interacts with planetary magnetospheres, guides the tails of comets, and carves a vast bubble in interstellar space called the heliosphere. Its touch reaches far past Pluto, forming the frontier between the Sun's influence and the cold domain of the galaxy. But in larger, hotter stars, the wind becomes a river of force. The intense radiation from their surfaces pushes on atoms and ions through absorption and scattering, driving them outward at speeds of thousands of kilometers per second. This radiative acceleration can strip a star of several solar masses before its life ends. Such winds are not random, they are shaped by metallicity, the abundance of heavier elements in the star's atmosphere. Metals absorb light more efficiently, amplifying radiation pressure and fueling stronger outflows. Thus, a star's chemical makeup decides how it will lose itself. As mass peels away, the star's internal balance changes. The core remains untouched, but the outer layers thin, altering surface temperature and luminosity. For massive stars, this gradual shedding can determine the form of their death. A star that loses enough mass may avoid becoming a red supergiant, and instead evolve into a stripped, blue-hot Wolf-Rayet star, whose exposed interior blazes with extreme ultraviolet light. These Wolf-Rayet stars are rare and brief, their winds among the most powerful known outflows so dense they glow, forming expanding nebulae of gas that drift like luminous shells around them. In less massive stars, the transformation unfolds more softly. As hydrogen fusion in the core slows, energy production shifts outward into a surrounding shell. The outer envelope expands, and the surface cools, turning the star red and immense. It becomes a red giant, a swollen echo of its former self. In this phase, the winds grow stronger, carrying away vast amounts of material over time. The process is slow but relentless. At first, dust condenses in the outer atmosphere, microscopic grains of carbon and silicate, and the star's light pushes these grains outward. The grains, in turn, drag gas with them, amplifying the wind. The star begins to fade behind its own haze, surrounded by the material it releases. These winds do not destroy, they prepare. The mass that drifts away will someday become the building material for new generations of stars and planets. Each atom expelled carries with it the memory of nuclear reactions deep within the parent star: carbon, oxygen, nitrogen, and other elements forged in fusion. In this way, the quiet outflow of a dying star becomes an act of creation. The wind is not an ending but a transfer, a continuation of balance on a larger scale. Astronomers trace these processes with care. Spectroscopy reveals the fingerprints of outflowing gas, the Doppler shifts that record its speed and direction. Space telescopes capture the infrared glow of dust-rich winds, while radio observatories detect the faint emissions of molecules carried into interstellar space. These data form a portrait of a star in the act of letting go, one that is both scientific and deeply human. The slow shedding of mass resembles aging in any form. The body lightens, the energy redistributes, the self begins to release what it no longer needs. Among massive stars, wind interacts with wind. When two giants orbit each other, their outflows collide, forming shock fronts that emit X-rays and sculpt spiraling patterns of gas. These colliding winds create structures of breathtaking complexity, arcs, plumes, and rings that stretch across light years. Even as they decay, such systems remain creative, weaving beauty from loss. In clusters, the combined effect of many stellar winds stirs the surrounding interstellar medium, compressing it and sometimes igniting new bursts of star formation. Thus, one generation's decline becomes another's genesis. In the Sun, too, the wind is not static. It rises and falls with the solar cycle, an 11-year rhythm tied to magnetic reversals. During active periods, the wind intensifies, carrying with it streams of energetic particles that strike Earth's magnetic field and paint the polar skies with auroras. Each shimmering curtain of green and violet light is a trace of our star's breath reaching across space. The calm and fury of the Sun are different expressions of the same continuous release. The philosophical weight of stellar winds lies in their quiet inevitability. Nothing in the cosmos truly keeps what it has. Every shining body gives something back to the dark. The winds are the universe's way of ensuring circulation, of preventing stagnation even in perfection. The material that leaves one star may drift for millions of years before finding another cradle. Dust that once floated in a red giant's outflow could later rest in the soil of a planet, or within a living cell that breathes beneath another star's light. In the end, wind defines transformation. It softens the line between life and death, between star and space. The heavens are not static jewels pinned to velvet. They are flowing, exchanging, breathing systems. A star's glow may seem constant, but it is slowly unraveling itself into the fabric of the cosmos, one particle at a time. The wind writes this truth in every direction, a whisper of matter becoming memory, a reminder that endurance in the universe is never absolute. It is always shared. In the deep heart of a mature star, time does not pass as it does on any world. It moves through cycles of fusion, one element giving way to the next, until the ladder of creation climbs no higher. Hydrogen becomes helium, helium becomes carbon and oxygen, and in the most massive stars, the sequence continues: neon, magnesium, silicon, each step demanding greater pressure, greater temperature, and greater courage from gravity itself. Yet there comes a final summit, a boundary that no natural fire can cross. That summit is iron. Iron is the quiet end of fusion. In the furnace of stellar cores, lighter nuclei merge to form heavier ones, releasing energy in the process. But when iron is reached, the arithmetic reverses. Fusing it no longer yields energy, it consumes it. The star, having built itself from the simplest particles into a cathedral of elements, finds that further building leads only to collapse. This realization is not conscious, but the result is inevitable. The calm that defined its long life begins to fracture. In smaller stars, the story ends gracefully. When the helium in their cores is spent, they shed their outer layers, leaving behind a dense, cooling ember, a white dwarf. But for the giants, the process is far more dramatic. Their cores, heavier and hotter, push through successive stages of burning with astonishing speed. What took millions of years with hydrogen now happens in mere days. Silicon burning, the final step before iron, can endure less than a week. Inside that brief moment, the star's interior becomes a layered sphere, shells of different elements fusing like the rings of an onion, each feeding energy to the next. This structure is majestic but unstable. The outer layers depend on the radiation from below to counter gravity. When the core stops producing energy, that support falters. Gravity, always patient, finally reclaims its due. The iron core, growing heavier, reaches a point where even quantum mechanics can no longer resist compression. Electrons, pressed into protons, create neutrons and neutrinos in a desperate transformation that releases nothing to the outside. the star's most vital defenses vanish in an instant. The collapse begins at incredible speed, the core falling inward at a quarter of the speed of light. It lasts only a fraction of a second. Then, as the core becomes dense enough to rival an atomic nucleus, it stiffens. An immovable core of neutrons halts the infall. The outer layers, still plunging inward, strike this barrier and rebound. The shock wave born in that collision travels outward, and the star explodes. What had been serene for millions of years ends in a single heartbeat of destruction. This is the moment known as core collapse, the threshold of supernova. Yet even in its violence, the process obeys subtle order. The energy of the explosion does not come primarily from the rebound itself, but from the flood of neutrinos released in the transformation. In that final second, the star emits more energy in neutrinos than the sun will radiate in its entire lifetime. Most of these ghostly particles escape into the universe unnoticed, but a small fraction interact with the collapsing material, reheating it and driving the blast outward. The dying star, in its last breath, uses the lightest of messengers to proclaim its end. This threshold, the formation of iron, and the sudden failure of fusion marks one of the most profound transitions in nature. It is the line where creation and annihilation meet. Until that moment, the star has been a giver, turning simple atoms into complex ones, radiating energy into the cosmos. Beyond it, the star must surrender everything it has built. The calm equilibrium that defined its existence becomes untenable, and the balance between pressure and gravity collapses inward into a single, irreversible conclusion. For all its inevitability, this transition is not tragic. It is the necessary bridge between generations. The explosion that follows scatters the heavy elements forged in the star's heart: carbon, oxygen, silicon, iron, into the surrounding galaxy. Every planet, every grain of dust, every living cell bears atoms once confined within such a dying core. The calm end of one equilibrium becomes the beginning of countless others. The final stages before collapse are short, but rich in structure. Within the last days, neutrinos stream freely through the dense core, cooling it faster than radiation can. The fusion shells outside fluctuate, creating turbulent waves that echo through the outer layers. Some of these waves may even preface the explosion, stirring the star's envelope in anticipation. It is as though the star, sensing the inevitable, loosens its grip on order, allowing chaos to bloom one last time before silence. Astronomers have caught glimpses of this transition in progress. Massive stars observed in the years or weeks before supernova have shown unexpected outbursts, shedding their outer material as if rehearsing the finale. When the explosion comes, that expelled gas becomes a glowing shroud around the corpse, lit from within by radioactive elements newly forged in the blast. For months, sometimes years, the debris shines with fading grandeur before dissolving into the dark. What remains a neutron star, or if the mass is high enough, a black hole, is the condensed memory of the life that once was. The physics of the iron threshold carries a profound symmetry. The same nuclear forces that once sustained the star now dictate its end. At every earlier stage, fusion released energy because the combined nucleus weighed slightly less than its parts. That tiny difference became light. With iron, the binding energy per particle reaches its maximum. There is no further gain to be had. In the language of the universe, iron is a full stop, the point where addition turns into subtraction. This law, so exact and unyielding, shapes the destiny of galaxies. Without it, there would be no explosions to scatter the elements, no enrichment of space, no complex chemistry from which life could arise. The inevitability of the iron limit ensures the continuity of creation. Stars die not because they fail, but because they must pass their work forward. Philosophically, the iron threshold is an image of surrender. Every force that builds must one day relinquish control. Every brightness carries within it the seed of its own dimming. Yet in that release lies renewal. The universe's beauty depends not on permanence, but on transition. The star, in ceasing to create energy, becomes the source of creation itself. Its death writes the script for matter's next form. Thus, the end of fusion is not a failure of fire, but its fulfillment. The iron core, cold to fusion but radiant in meaning, becomes the hinge between order and transformation. What follows will be violent and magnificent, but within that violence lies continuity. Every calm light seen in the night sky is a reminder that even peace, in the cosmic sense, is never static. It is a moment balanced between beginnings and endings, a breath taken before release. When a star finally reaches the iron threshold, its long patience gives way to a moment so brief it defies the scale of its own history. In less than a heartbeat, the steady inward pressure of gravity overwhelms the resistance of matter itself, and collapse begins. What follows is one of the most astonishing events in nature, an explosion that appears to violate calm but, in truth, extends the same cosmic rhythm into another form. This is the supernova. The name evokes catastrophe, yet at its core lies a paradox of generosity. The dying star releases more energy in a single instant than billions of suns emit in their entire lives. It does so not out of fury, but because the rules of balance demand that what once was bound must be set free. The elements forged over millions of years are cast into the dark, seeding the future with possibility. The universe, through destruction, ensures renewal. The sequence unfolds with exquisite precision. When fusion can no longer support the weight of the core, gravity takes command. The collapse accelerates until atomic nuclei are crushed together and electrons are forced into protons, forming neutrons and releasing an ocean of neutrinos. The temperature rises to billions of degrees. The density soars beyond comprehension. The outer layers, still in freefall, slam against the now solid neutron core and rebound outward. The shock wave races through the star, gaining strength from the energy carried by those escaping neutrinos. The moment the shock breaks the surface, the star's brightness surges by a factor of 1 billion. In distant galaxies, these explosions briefly outshine everything around them. For observers on Earth, a supernova is not just an event, it is a revelation. The night that once hosted a faint, steady point suddenly flares into a beacon bright enough to cast shadows. Ancient astronomers recorded such apparitions, stars that appeared where none had been before, burned for weeks, then faded forever. What they witnessed was the universe rewriting itself. The light from these deaths has traveled across space for millions of years, arriving just in time for human eyes to see the proof that endings can be luminous. Each supernova is an alchemy. In the fraction of a second when nuclei are crushed together by the shock, conditions become extreme enough to forge elements heavier than iron, cobalt, nickel, copper, silver, gold. These atoms are made in a furious rain of neutrons, captured faster than decay can undo them. The process, known as the R process, is nature's ultimate forge. The jewelry of planets, the metal in machines, the core of the Earth itself all owe their origin to these brief and violent births. Even the iron in blood, the gold in a wedding ring, and the calcium in a bone were once scattered by a dying star. The explosion does not destroy meaning, it disperses it. As the outward blast expands, it collides with the material previously lost to stellar winds, forming luminous shock fronts that radiate in every color. These supernova remnants persist for thousands of years, veils of gas and dust illuminated by their own motion. Through telescopes, they appear as filigree structures of unimaginable delicacy, webs of crimson and teal, like smoke caught in slow motion. Every thread is an echo of the star's final breath. The Crab Nebula, born from such an event, still glows nearly 1,000 years after its explosion, its filaments moving outward at supersonic speeds. There are different families of these endings. Some occur in solitary massive stars that collapse under their own gravity. Others are born in companionship binary systems, where one star, already reduced to a white dwarf, steals matter from its partner until a critical limit is reached and runaway fusion ignites its surface. The resulting detonation, a type Ia supernova, is so uniform in brightness that it serves as a cosmic ruler, allowing astronomers to measure the expansion of the universe. Even in death, stars contribute to our understanding of time and distance. Among the most mesmerizing are the kilonovae collisions between neutron stars, the compact remnants left behind after supernovae. When two such remnants spiral into each other, their merger sends ripples through space-time itself, gravitational waves that ring across the cosmos. For a moment, matter is compressed beyond nuclear density, and again heavy elements are forged in abundance. The light from these collisions is short-lived but vivid, fading within days yet enriching galaxies with precious metals. Each event is a whisper of how the cosmos replenishes its own complexity. Despite the grandeur, the mechanisms of supernovae are still studied with awe and uncertainty. Computer models trace the intricate dance of turbulence, magnetic fields, and neutrino flows that determine whether a collapsing star will explode or implode silently into a black hole. What seems like chaos conceals hidden symmetry, the fine-tuning required to propel the shock wave outward without losing it to gravity's grasp. A small change in conditions can decide whether the star dies in brilliance or disappears in silence. The remnants left behind are monuments of physics. A neutron star, only a few tens of kilometers wide, contains more mass than the Sun, its matter packed so tightly that a spoonful would outweigh a mountain. Some of these remnants spin rapidly, emitting beams of radiation that sweep through space like cosmic lighthouses, pulsars, the metronomes of the galaxy. Others collapse entirely into black holes, where gravity folds space upon itself, leaving only an event horizon and the ghost of the star's former self. The energy of a supernova radiates through interstellar space, compressing clouds and triggering new rounds of star formation. Shock waves pass through nebulae, stirring them to collapse, and the cycle begins again. The ashes of one generation become the seeds of the next. Thus, the calm order that seemed lost in explosion is restored on a larger scale. The galaxy breathes, inhaling destruction, exhaling creation. Philosophically, the quiet gift of the supernova is continuity. Nothing that exists in the universe is spared from change, yet nothing is truly lost. The energy released in death becomes the foundation of future order. The violence we see from afar is not chaos, but conversion, a translation of matter into light and of light into memory. The explosion is loud only to our eyes. To the universe, it is simply the completion of a long-held promise. In the end, every glowing remnant, every gold ring, every iron atom in the blood testifies to that ancient truth. The universe's calm does not exclude fire. It is built upon it. What appears as destruction is an act of balance, returning the renewal of the cosmic covenant between energy and matter. The supernova, in all its radiance, is not an ending. It is the universe breathing out. When the final echo of a supernova fades, what remains is not silence but persistence. The star that once flooded space with its light becomes something smaller, stranger, and more enduring than before. These remnants, white dwarfs, neutron stars, and black holes, are not corpses but transformations. They are the condensed outcomes of equilibrium taken to its last expression, where the rules of matter stretch to their furthest limits without breaking. In their quiet endurance, the universe finds new ways to remember itself. The simplest of these relics are white dwarfs. They are the remnants of stars like the Sun, stripped of their outer layers after long lives of fusion. What is left behind is the core, a sphere of carbon and oxygen the size of Earth, yet containing half a sun's mass. No nuclear fire burns within. The light they emit is merely the fading glow of stored heat. But despite their exhaustion, white dwarfs do not collapse. They are held up by a different kind of pressure, one born not from temperature but from quantum mechanics. This pressure, called electron degeneracy, arises because electrons resist being squeezed into the same state. In the dense interior of a white dwarf, every quantum seat is already occupied, and further compression meets a powerful resistance. It is an invisible scaffolding that keeps gravity in check. The equilibrium is fragile, yet absolute. Add too much mass, and even the electrons cannot bear the burden. There is a precise limit, about 1/4 times the mass of the Sun, known as the Chandrasekhar limit. Beyond it, collapse resumes, and the white dwarf transforms again into a neutron star, or, if the fall is complete, a black hole. For those that remain below that threshold, time becomes slow. White dwarfs cool for billions of years, fading from white to red to black, as their stored energy seeps away into space. None have yet reached full darkness. The universe is still too young for that. They are cosmic embers, reminders that even in decay, structure persists. Some, locked in binary systems, pull matter from their companions, rekindling for a brief time into novae bursts of light caused by renewed fusion on their surfaces. These flashes are small rehearsals of lost youth, short but brilliant. Then the calm returns, and the cooling continues. Neutron stars are another order of being. They are the hearts of massive stars, crushed by supernova collapse into spheres barely 20 kilometers wide. Inside, gravity has fused electrons and protons into neutrons, creating a substance so dense that a teaspoon of it would outweigh a mountain. In this extreme state, the laws of matter bend toward mystery. The neutrons themselves are packed so tightly that quantum degeneracy once again resists further collapse, this time through neutron pressure. The equilibrium is a fortress built on the smallest scales. From their compactness comes power. Many neutron stars spin rapidly, conserving the angular momentum of the collapsed core. As they rotate, their magnetic fields amplified a trillion-fold sweep through space, generating beams of radiation. If Earth lies within the path of these beams, we see them as pulses of radio waves, repeating with clock-like precision. These are pulsars, the metronomes of the cosmos, ticking out the seconds of an ancient death that never quite concludes. Some spin hundreds of times each second, their rhythm so stable that they rival atomic clocks. In their flickering, the universe keeps time for itself. Not all neutron stars remain quiet. When two orbit each other, their immense gravity sends ripples through space-time gravitational waves that stretch and squeeze the very fabric of the cosmos. When they finally merge, they release energy detectable across the universe, confirming predictions made a century earlier. In that instant, the line between mathematics and experience disappears. The equations of relativity come alive. The waves carry with them news of collisions that happened millions of years ago, whispering of the universe's memory written in motion. Beyond the neutron star lies the final transformation, the black hole. Here, gravity completes its slow conquest. The collapse continues until no known force can halt it. Matter falls inward beyond a boundary where escape is impossible. This invisible border, the event horizon, marks the point at which space and time trade roles. To move forward is to fall inward. The core itself shrinks to a singularity, a region where density becomes infinite and the equations that describe the universe falter. What remains is not a thing but a condition, a curvature of space-time so deep that even light cannot find its way out. Black holes are the universe's quietest paradoxes. They emit nothing, yet their presence is unmistakable. Their gravity bends light, distorts time, and anchors the motion of entire galaxies. Around them, matter falling inward forms, accretion disks that heat to billions of degrees, emitting X-rays before disappearing into the dark. Some spin so fast that they drag space itself around with them, twisting the geometry of the universe into a whirlpool. Their existence confirms that nature does not fear extremes. It embraces them as part of its continuum. Despite their darkness, black holes are not beyond comprehension. In 2019, the Event Horizon Telescope captured the first direct image of a black hole's shadow, a glowing ring of light bent by gravity around an unseen center. The image revealed more than a scientific triumph. It was an aesthetic revelation. The void, framed by fire, became a symbol of balance, preserved through paradox. Where matter ends, geometry continues. Each of these remnants, white dwarf, neutron star, black hole, represents a different form of endurance. The white dwarf resists gravity through quantum pressure, the neutron star through nuclear density, the black hole through surrender, allowing collapse to complete itself and become spacetime's own geometry. In every case, the universe finds a way to keep existing without breaking its laws. Equilibrium persists, but in new forms, at new depths. The transformation from star to remnant is not only physical but philosophical. It demonstrates that even death is a rearrangement, not a negation. The light of a main sequence star, the explosion of a supernova, and the silence of a black hole are all phases of the same conversation between matter and gravity. The calm of the cosmos is not a flat line but a pulse contraction followed by release, brightness followed by stillness. One day, long after galaxies have dimmed, the universe will be filled mostly with such remnants, faint white dwarfs cooling into darkness, neutron stars spinning in solitude, black holes drifting like invisible anchors. Yet even then, balance will hold. The forces that once shaped light will continue to shape emptiness. And in that final quiet, when matter itself has become memory, the echo of every star's endurance will remain. That peace, in the universe, is never the absence of motion, but the mastery of it. The instruments that now gaze into the universe are not built merely to look, they are built to listen, to weigh, to count, and to feel the faint tremors of events that occur far beyond the reach of light. The study of stars, once a discipline of observation and wonder, has become a collaboration between gravity, photons, particles, and geometry itself. Through the patient ingenuity of these tools, humanity has learned not only what stars are, but how they change, how they end, and how their memory continues through the fabric of the cosmos. The first tool remains the telescope, but the telescope has evolved far from the mirrors that once caught starlight on mountaintops. Space-based observatories have lifted vision beyond the blur of air and weather. The Hubble Space Telescope, with its patient eye above the atmosphere, has mapped the lives of stars in other galaxies, capturing their births in glowing nurseries and their deaths in spiraling veils of debris. Each image, still and silent, hides millions of years of movement. Hubble's successor, the James Webb Space Telescope, sees even deeper, not with visible light, but with infrared eyes tuned to the warmth of dust and the cool glow of distant beginnings. It can peer into regions where stars are still forming, wrapped in dark clouds impenetrable to ordinary sight. There, it reveals the first flickers of fusion, the moments when gravity turns to light. Beyond imagery, there is motion recorded through soundless measurement. The Gaia mission has transformed the Milky Way from a map of dots into a living, rotating system. By measuring the precise positions and movements of more than 1 billion stars, Gaia has allowed astronomers to trace their orbits backward and forward in time, revealing how galaxies breathe and evolve. Each star's motion carries the fingerprint of gravitational interactions, the echoes of ancient collisions and spiral waves that ripple through the galactic disk. For the first time, the story of stellar life is not only seen but reconstructed in motion, as if the universe were revealing its own autobiography. Light, however, tells only part of the tale. To understand the hidden forces that shape stars, new senses had to be invented. Neutrino observatories, buried deep underground or beneath Antarctic ice, wait for particles that can pass unhindered through entire planets. These elusive messengers come directly from the hearts of stars and from the instant of their deaths. When a supernova erupted in a neighboring galaxy in 1987, a handful of neutrinos arrived at Earth hours before the light. They had escaped the collapsing core long before the shock reached the surface. In those few particles, the universe whispered its process in real time, proof that we could listen to creation through matter itself. Then came the detectors of gravitational waves. Long predicted by the mathematics of relativity, these ripples in spacetime are caused by the most extreme events, collisions of black holes, mergers of neutron stars, or the oscillations of the early universe itself. For decades, they existed only as theory, faint curves on chalkboards. But in 2015, the twin LIGO observatories, enormous laser interferometers capable of measuring distortions smaller than a proton's width, recorded the first passing wave. The signal lasted only a fraction of a second, but it carried within it the vibration of 2 black holes spiraling together 1 billion light-years away. It was the faintest sound the universe had ever made, and yet it confirmed a century of thought. Since then, a global network of detectors, LIGO in the United States, Virgo in Italy, KAGRA in Japan, has begun to listen continuously. Each new detection adds a note to a growing cosmic symphony. These waves reveal what light cannot: the invisible dance of dark remnants, the pulse of gravity itself. They let us hear the universe directly, without mediation by matter or radiation. To study them is to touch the cosmos through its very structure. The same integration of senses extends to other realms. X-ray observatories, such as Chandra and XMM Newton, reveal the searing energy around neutron stars and black holes, where matter falls inward faster than it can radiate away heat. Gamma-ray detectors catch the brief, violent flashes that signal the birth of black holes or the merging of neutron stars. Radio telescopes stretch their long arms across continents, joining signals in unison through interferometry to image cosmic jets and measure pulsar timing with astonishing precision. The result is a kind of orchestral unity, every wavelength, every particle, every vibration contributing a note to the grand score of stellar life. The laboratory for these investigations is not a single place but an entire planet. The human species, scattered across observatories and space stations, participates in a collective act of attention. High in Chile's Atacama Desert, arrays of radio dishes turn in unison beneath skies so dry and clear that even the Milky Way casts shadows. Beneath Antarctic ice, detectors wait for neutrinos older than Earth itself. In orbit, telescopes trail the planet like patient companions, their golden mirrors collecting light that began its journey before humanity had names. The instruments differ in design but share a single intention to understand how the universe keeps its balance. Science, in this mature form, becomes less a hunt for surprise and more a practice of listening. Each instrument contributes not to conquest, but to harmony, to the slow realization that the cosmos is coherent in all its parts. When a gravitational wave passes through the Earth, every molecule, every mountain, every star quivers slightly in agreement. We live inside that resonance without noticing it, as fish live within water. Philosophically, these tools reveal something beyond data. They show that to study the universe is to mirror its patience. The detectors that sense neutrinos or gravitational waves must wait years for a single event. They are built on the assumption that the cosmos is generous enough to reveal itself in its own time. Their silence is as important as their detections. The waiting is the method. Through them, humanity's understanding of stars has become almost intimate. We no longer see them only as distant fires, but as systems whose hearts can be mapped, whose histories can be traced, and whose deaths can be heard through the trembling of space-time. The instruments have turned our planet into an extension of the senses, a lens, an ear, a fingertip pressed against the pulse of the universe. In this sense, the new tools of astronomy are not separate from the stars they study. They are continuations of the same law, the desire for equilibrium. Each detector, each mirror, each quiet chamber underground seeks balance between noise and signal, between waiting and discovery, just as a star balances gravity and light. Science and the cosmos move by the same principle: persistence without haste, curiosity without rest. When the great instruments of observation had mapped the stars and the theories had stitched their lives into equations, another realm opened, the realm of speculation. Science, when it reaches the border of certainty, begins to hum with imagination. Beyond the known cycles of birth, life, and death lies a territory of quiet hypotheses, ideas about what else the universe might permit if its laws were nudged, or if its constants were tuned by even the smallest degree. The life of stars, so seemingly complete in explanation, still hides corners of mystery, and in those corners, speculation begins. Some physicists imagine that not all stars are made of the matter we know. Deep in the early universe, before atoms formed, the cosmos was filled with dark matter, invisible, massive, and cold. Perhaps, they suggest, this unseen substance once condensed to form the first generation of dark stars. These would not shine by nuclear fusion but by the annihilation of dark matter particles in their cores, releasing energy without consuming hydrogen. Such stars might have grown to enormous sizes, hundreds or thousands of times the mass of the Sun, glowing faintly in infrared light before collapsing into black holes that seeded galaxies. If they existed, their relics may still haunt the centers of galaxies today, disguised as ordinary darkness. Others turn their attention to the substances within stars that remain hypothetical. Actions particles proposed to solve a symmetry problem in quantum physics might be produced in stellar cores, slipping silently through matter and carrying away energy. If such particles exist, they could alter how stars cool, how white dwarfs fade, or how supernovae ignite. Observatories on Earth already search for these invisible travelers, knowing that to detect even one would transform our understanding of both particle physics and stellar life. There are speculations, too, about new states of matter. Inside the hearts of neutron stars, densities exceed the limits where atomic nuclei can remain intact. What then becomes of matter there? Some theorists propose a transition to quark matter, where neutrons dissolve into their constituent quarks, forming a soup of fundamental particles. Others imagine strange stars, composed of exotic combinations of up, down, and strange quarks bound together by the strong force. These objects, if real, would shimmer at the edge of comprehension, neither star nor atom, but something between the two. A handful of puzzling observations hint at their presence, but confirmation remains elusive. Magnetars, another exotic possibility, already blur the line between science and poetry. They are neutron stars with magnetic fields so powerful that a single spark would erase data from every hard drive on Earth. Their fields twist the very fabric of their crusts, producing starquakes that release bursts of X-rays and gamma rays visible across galaxies. These monsters exist, but their origins challenge understanding. How can nature wind a magnetic field to such extremes without tearing itself apart? The answer lies in equations not yet complete, in regions of theory where quantum mechanics meets general relativity and both fall silent. Even the familiar rules of fusion invite speculation. What if variations in the fundamental constants, the fine structure constant, the strength of gravity, the ratio of electron to proton mass, were different by even a fraction? Stars as we know them could not exist. Hydrogen might never fuse, or fusion might proceed so quickly that equilibrium could not be sustained. The very existence of long-lived stars depends on the universe being tuned with extraordinary precision. Whether this balance arose by necessity, coincidence, or design remains one of the most profound questions in cosmology. The boundary between speculation and observation is continually tested. The James Webb Space Telescope, with its infrared sensitivity, may already be seeing the first generation of stars, the long-theorized Population 3. These would have formed from pure hydrogen and helium before metals existed, their fusion processes faster and their deaths more violent. If confirmed, they would be the ancestors of every subsequent generation, the universe's first attempt at starlight. Detecting their signatures, the faint fingerprints of their explosions or the radiation from their remnants, would connect the beginning of cosmic time with the stars we see now. Another realm of inquiry concerns the final fate of stars in an expanding universe. Long after fusion has ceased and black holes dominate, new forms of star-like objects might emerge from decay and collision. Some cosmologists foresee the black dwarf supernova, an event so far in the future that it stretches the imagination beyond comfort. Over trillions of years, the cold remnants of white dwarfs might accumulate energy through quantum tunneling until, one by one, they explode in final bursts of light, briefly rekindling a dying universe. The idea is theoretical, almost mythic, yet mathematically consistent. It suggests that even in the darkness beyond measure, the cosmos will not forget the art of illumination. Speculation also stretches to the cosmic web itself, the notion that stars may not be the only form of luminous balance. Perhaps there are structures formed by dark energy, or by collective quantum effects on galactic scales, unseen because they emit neither light nor radiation. Perhaps entire families of objects live in those shadows, obeying physical laws yet untouched by ordinary perception. To entertain these ideas is not to abandon science, but to honor its spirit. The universe rewards imagination disciplined by evidence, and it is often speculation that lights the path toward discovery. Still, the most elegant speculations do not simply multiply possibilities, they deepen reflection. What is a star, truly? Is it merely a thermonuclear machine? Or is it the universe's most refined form of balance, an embodiment of stability achieved through contradiction? Perhaps other kinds of equilibrium exist, invisible yet analogous. Perhaps consciousness, life, and matter are all variations of the same principle, energy learning how to persist. The new physics that astronomers seek, dark matter, dark energy, exotic particles, may eventually explain the hidden half of the cosmos. But even if every equation were solved, the sense of wonder would remain untouched. Science does not erase mystery, it refines it. The act of understanding transforms the unknown not into certainty, but into a deeper kind of beauty. In the speculations surrounding stars, the universe seems to offer a quiet confession. It has never stopped inventing. Every discovery uncovers another question. Every answer opens a door to new awe. The stars we see are only one version of what could be, one chapter in a book that no one will ever finish. The cosmos is not static. It is an unfinished poem, written by the laws of physics and edited by imagination. In the hush that follows every calculation and the glow of every image, a question remains not of data, but of meaning. What, finally, do the lives of stars tell us about existence itself? Beneath the formulas, beneath the physics of pressure and radiation, there is a more quiet truth, that peace, not conflict, sustains the universe. The star is not a battlefield. It is a truce, a sustained dialogue between opposing desires, gravity's urge to fall, and light's urge to escape. Every luminous point in the night sky is a record of that conversation continuing without end. The life of a star is the most patient expression of balance ever written. From collapse to ignition, from stability to decay, it embodies the principle that endurance arises not from force, but from harmony. It does not defy gravity. It collaborates with it. It does not rage against darkness. It illuminates it by being constant. Each stage of its existence, from the cloud to the cinder, reveals the same idea in different language, that equilibrium is not stagnation, but the refinement of motion into stillness. Humanity has long looked at the stars and found metaphors for itself. Empires saw omens, poets saw souls, travelers saw direction. But behind those interpretations lies something more elemental, a recognition that the same laws shaping starlight shape us. We, too, are the outcome of balance. The atoms in blood and bone were once scattered by exploding suns. The warmth that fuels every breath is the echo of fusion carried through time. To understand the star is to understand that life is built from persistence, not permanence. The star dies, yet its materials endure. There is a profound humility in this realization. The star does not choose to shine. It shines because its nature is to maintain equilibrium. The universe does not rush toward completion. It unfolds, patiently, according to laws that favor continuation over conclusion. Even decay is a kind of grace, a release that feeds what follows. The galaxy glows because countless stars have already given themselves to its dust. The calm of the night sky is not emptiness, it is inheritance. The tools and theories that have revealed so much, the telescopes, the detectors, the equations, all serve one quiet purpose: to trace the rhythm of balance across scale and time. From the smallest vibration in an atom to the slow rotation of galaxies, the same principle repeats. Nothing persists by dominance alone. Everything survives by reciprocity. The star lives because gravity allows light to push. The universe endures because expansion allows matter to cool. Existence is an agreement between opposites, a long accord sustained by mutual concession. This understanding invites reflection beyond science. Perhaps serenity, whether cosmic or human, is found not in victory but in proportion, in the art of giving as much as one receives. The star loses mass to light, yet that loss is its beauty. It spends itself into illumination. Its peace depends on surrender. If there is a lesson written in the sky, it may be that stillness does not mean inaction, but the perfect alignment of effort and restraint. Consider the starlight that reaches a quiet shore at night. It left its source long before humanity existed, crossing the vacuum unhurried, patient beyond comprehension. By the time it touches an eye, the star that released it may already have changed or vanished. Yet the light endures. It arrives unchanged, carrying the memory of conditions long past, proof that the universe remembers itself through motion. In that realization lies a calm both scientific and spiritual. Nothing truly disappears, it only transforms. The philosopher and the physicist meet in that point of understanding. For both, the cosmos is not chaos but coherence. Order emerges not by force but by symmetry. The star teaches that being and becoming are the same act, that time itself is not an enemy but a participant in creation. Its steady glow is not a defiance of entropy but a measured participation in it, a way of turning inevitable decay into prolonged grace. And yet, for all their vastness, stars remain delicate. A tiny change in their composition, a slight shift in gravity, a whisper of imbalance could end them. That fragility is what makes their endurance so moving. The universe's grandeur rests on conditions fine enough to be almost impossible, and yet here it is thriving, glowing, speaking across distance. The miracle is not that stars exist, but that they persist despite the odds. Perhaps that is the deepest comfort the cosmos offers, that balance, once found, can hold through unimaginable stretches of time. The stars are not eternal, but their pattern is. Each generation rises, shines, and yields, composing a rhythm that never falters. Even when the last light fades billions of years hence, the echo of that rhythm will remain in the geometry of space itself. The cosmos does not end. It slows, cools, and remembers. In that far future, when galaxies have dimmed and matter grows thin, there will still be motion particles drifting, quantum fields whispering their low hum, black holes evaporating into light. The same principle will still govern. The exchange between gravity and energy, loss and renewal, silence and continuation. Even darkness will not be absolute. It will be filled with the residue of all that once burned. To stand beneath the night sky and think of these things is to participate in them. The boundary between observer and observed dissolves. We are made of the same hydrogen, once fused in distant cores, our thoughts powered by the same physics that keeps suns alive. To look up is to look inward. To study the stars is to remember what endurance feels like. So let the mind rest on that image. A star, balanced perfectly between gravity and fire, giving without exhaustion, existing not through dominance but through harmony. Its calm is not silence but song. Its glow is not pride, but patience. The star's life, seen from beginning to end, is the universe learning how to breathe. And in that breath lies the quiet truth of everything that peace is not found at the edge of motion, but at its center.